In our previous video, we looked at how we can use a partition function to find the average energy of an ensemble, and if we have a large enough ensemble, we can say that is going to be equal to the observed energy that we see for our system. Now, what are some of the other macroscopic quantities that we can calculate? Well, one pretty simple one is the heat capacity. So this is something we have discussed in the thermodynamics section of this class. And just as a reminder, this is equal to du dt at constant V, right? What's our change in internal energy as a function of temperature, keeping the volume constant for the constant volume heat capacity. And since we said that the internal energy that we observe is equal to the average energy, we can say this is the same as the average energy dt holding V constant. And in the previous video, we showed that the molar heat capacity, CV bar, is equal to 3/2 N kBT. And so if we take the, sorry, that's not CV bar, that's the average energy. But our average energy is equal to this. So if we take the derivative with respect to temperature, we get that we have 3/2 CV bar, CV is equal to 3/2 N kb. And if we want to make this a molar quantity, we set N equal to Avogadro's number, and we will get 3/2 Avogadro's number times kb, or 3/2 R. And this is specifically for a monatomic ideal gas, because that's the partition function we were looking at before. And this is exactly the same heat capacity we would expect via classical physics for a monatomic ideal gas. So we get 1/2 R contribution to the heat capacity for each dimension for x, y, and z. Okay, and so if we can calculate this average energy, we can use this relationship to also get to heat capacities. And so if you have more complicated expressions for for the average energy of your system, you'll get more complicated expressions for the heat capacity. What are some other macroscopic quantities we can look at? Another one is pressure. So for example, we won't show this, but the pressure of a specific state, J, which will be a function of the number of particles in the volume, can be shown to be equal to minus dEj dV at constant n. We're not going to show this, but you can derive this. And so this is saying the pressure of a specific, right, J here again being a specific system that we have, is the derivative of the energy with respect to volume. And so we can do the same thing that we did with energies and say, okay, well, what's the average pressure? The average pressure of our system is equal to the sum over the probability of each state times the pressure of each state. And we can go ahead and plug in our definitions for these. So we have e to the minus beta e sub j over q, that's our probability, times this derivative that we have here, d ej dv at constant n. So we add up all these terms. Now we can go ahead and rewrite this in terms of partition functions, and so we'll show that here. Let's look at dq dv at constant n and beta. So holding the temperature constant, remember beta is directly related to temperature. So that's the derivative with respect to v of the partition function, which again is equal to e to the minus beta e sub j. Okay, so we take the derivative here, we get minus beta, because our energies are going to depend on volume in some ways. So we'll have, we don't know what the derivative is, but we have dEj dV at constant n times e to the minus beta e sub j. And this is using the properties of derivatives of exponentials. So we have the chain rule going on here, right? We take the derivative of this function times the derivative of what's inside of here. So that's where this negative beta is coming from. And then, sorry, the negative beta is coming from the derivative of the exponential. We get beta back as well as the exponential. And the derivative of what's inside here is dE dV at constant n. Okay, regardless, what we have here is, this is our, let me use a different color here. This is related to our individual pressures. And so we can add all those together. And this function is essentially this right here. So we can say that the average pressure is equal to kBT over Q, dQ, dV at constant n and beta, or that kBT, just rewriting this derivative, d log Q dV constant n and beta. Right, so this is looking at our expression up here for the average pressure and relating it to this dQ dV right here. Because we end up with a term that's adding together all of the, anyway, we can see the relationship here. Okay, and so this gives us a way to calculate pressures. So just real quick, let's do this again. Let's use this equation. I don't care so much about the derivation. What I care more about is being able to apply this equation. So let's look again at our monatomic ideal gas partition function, where we have Q is Q to the n raised to the n divided by n factorial, where little q is equal to 2 pi m over h squared beta raised to the 3/2 times volume. And we need to take plug it into this equation here. So a natural log of big Q is equal to n log little q minus log of n factorial. So we've seen this before. And now we can go ahead and write this out, plugging in little q. This is n times natural log of 2 pi m over h squared beta raised to the 3/2 plus n log v minus log of n factorial. And if we notice this time, our derivative is in terms of volume. So this is the only part that has volume in it. And so when we take the derivative, the other terms are going to go to 0. So d log q dv, holding n and beta constant, is simply n over v. That's pretty straightforward. Or we can say that the pressure then, coming back up to our equation here, is kBT times this derivative. So our average pressure, or our pressure, is equal to kBT times n over v. And this is, this is the ideal gas law, right? That PV equals n kBT. Or we can, if we multiply by Avogadro's number, we can write this as nRT instead, right? If we express things in moles instead of in numbers or particles. All right, so we can show that our definition for the partition function for an ideal gas law is consistent with these definitions we come up with partition functions. So that's another example of how we can use partition functions to find another macroscopic quantity, in this case the pressure.